In this chapter and in the coming lectures, we are going to talk about breadth-first search graph traversal algorithm. Of course, you may pose the question that why are we talking about breadth-first search, depth-first search and graph algorithms if we are after artificial intelligence related approaches? And we will come to the conclusion that with the help of these graph algorithms, we can solve several artificial intelligence related problems. So this is why we have to talk about breadth-first search and depth-first search. Okay, so first of all, we have a graph with v vertices and e number of edges, and the aim of breadth-first search is to visit every single vertex exactly once. Breadth-first search visits the neighbors and then the neighbors of these new vertices until all nodes are visited. What is the running time complexity of this approach? Of course, we visit every single vertex exactly once, and because these vertices are connected by edges, of course we have to visit the edges as well. So the running time complexity is ordo v plus e, where v is the number of vertices, e is the number of edges. So we can come to the conclusion that breadth-first search has a linear running time complexity. What about the memory complexity? The memory complexity is not that favorable as we have to store several references. We are going to talk about it in the coming lectures. So what do we have to do? We have to define a starting vertex, in this case vertex A, and of course we have to visit all the neighbors. So there are two vertices, vertex B and vertex C, so we have to visit them and we have to visit all the neighbors of these vertices. Of course we have to make sure that we are not going to visit a vertex that has already been visited. So we visit vertex D, then vertex E and vertex F. Okay, so what's crucial that because breadth-first search needs a lot of memory, usually depth-first search is preferred. Of course, there are several applications of breadth-first search, but if we can use both breadth-first search and depth-first search, then depth-first search is preferred because of the memory complexity. Breadth-first search has a huge advantage. It constructs the shortest path. By the way, Dashka's algorithm essentially does a breadth-first search when all the edge weights are initialized to be 1. So we can find the shortest path in a graph with breadth-first search if all the edge weights are 1, and of course it is not possible with depth-first search. So this is one crucial advantage of breadth-first search. And finally, breadth-first search relies extremely heavily on the Q abstract data type we will see during implementation. Okay, so let's take a look at the source code. We are going to implement something like this. We have to define a starting vertex. We have to use a Q abstract data type. First, we have to set it to be visited. Of course, we have to add the starting vertex to the queue. And while the queue is not empty, we take the first item we have inserted. This is why we use a Q abstract data type with the first in, first out structure. So we get the first item we have inserted. We visit every single neighbor, and if we haven't visited that given vertex, then we set it to be visited and we add that vertex to the queue. And of course, the algorithm terminates when there are no more vertices in the Q abstract data type. So let's take a look at a concrete example. Of course, we have a graph with all the vertices A, B, C, D up to G. And of course, we have a Q abstract data type where we can store the references or the objects in a FIFO manner. What does it mean? FIFO stands for first in, first out. The first item we insert is the first item we take out. And this is exactly what we need during breadth-first search. So we have to define a starting vertex, in this case vertex A. We insert vertex A to the queue, so this is going to be the first item. And then what do we have to do? We have to take the first item we have inserted, this is vertex A, and we set it to be visited, and we consider every single neighbor. Vertex A is connected to vertex B and vertex C, which means that we insert these objects to the Q abstract data type. By the way, you may guess that the order doesn't matter. In this case, we have inserted vertex B first and then vertex C, but of course it may happen that vertex C is the first one and vertex B is the second vertex present on the queue. So the order in which we visit these vertices doesn't matter. Okay, so what do we have to do? We have to take the first item we have inserted onto the queue. It is vertex B, so this is the first item, and we visit that given vertex, and we visit all the neighboring vertices, vertex D and vertex E. We insert these vertices to the queue abstract data type. At the moment, we have 3 references on the queue, vertex C, vertex D, and vertex E. What do we have to do? We have to take the first item we have inserted, which is vertex C, we set it to be visited, we visit all the neighbors of vertex C and insert them onto the queue. Then we take the vertex D and we set it to be visited. There are no neighboring vertices, so we keep going, we visit vertex E, there are no neighbors, we keep going and visit vertex F, and finally we visit vertex G. So what's crucial that breadth first search visits the vertices on a layer by layer basis. We have started with the root node, then we have visited the next layer, vertex B and vertex C, then we have visited the next layer, vertex D, vertex E, vertex F, and vertex G. Okay, so this is a fundamental feature of breadth first search. Let's take a look at another example. We have to define a starting vertex, in this case vertex C, and we insert it onto the queue. So we take the item from the queue, this is vertex C, and we visit all the neighbors, vertex B, vertex D, and vertex E. Again, the order of the items doesn't matter. It may happen that we insert vertex B, vertex D, and vertex E. Okay, in the next iteration we have to take the first item we have inserted, which is vertex E, we set it to be visited, and we visit all the unvisited vertices. Of course, you may guess that we don't have to visit vertex D because vertex D has already been visited. It is present on the queue. So we visit vertex H and we insert it onto the queue. We keep removing items from the queue. This is the vertex D, and we visit all the unvisited vertices, vertex A in this case. Then we keep going and we visit vertex B because of course there are no neighbors of vertex A. So we get the first item we have inserted onto the queue, which is vertex H in this case, and we visit vertex H. Of course, we set it to be visited, and we visit all the unvisited neighbors of vertex H. Of course, we don't have to consider vertex E because vertex E has already been visited, but we have vertex F and vertex G. So we push these vertices onto the queue. Then what do we have to do? We have to remove the first item, which is vertex A. We set it to be visited. We have already considered all the neighbors of vertex A, so we keep going. We visit vertex G and set it to be visited. And because there are no unvisited vertices, it means that we have to keep going. We get vertex F and we set it to be visited, and the queue becomes empty, as you can see. If the queue is empty, this is the end of the algorithm. Okay, so that's all about the breadth first search graph traversal algorithm. We need a queue abstract data type in order to implement this algorithm. This is exactly what we are going to do in the next lecture during the implementation. Thanks for watching.